Hi everyone. In this video I want to talk about one reaction, Williamson Ether Synthesis. It is the preferred way to make ethers. This is reaction M. And it's named after, well, obviously Williamson. And this is why I put ethers in the same category or same unit as alcohols, because we're going to start out with an alcohol. It could be primary, secondary, or tertiary. It really doesn't matter. Okay, I made this primary. And the first reaction is a deprotonation. And we're going to use several different reagents to do the deprotonation. The first one I'm going to use is sodium hydride. If you think about what's going to happen in the first reaction, we're just going to deprotonate the hydroxyl group and get the O-, the alkoxide. And then that alkoxide is going to attack an alkyl halide. And this is where we want to be sure that the alkyl halide is either primary or a methyl halide. So that's the requirement for Williamson ether synthesis, that the alkyl halide has to be a primary alkyl halide or a methyl halide, or we could just represent that with CH3X, CH3Br, or CH3Cl. All right, so the product is going to be an ether, obviously. And here's the carbon that's being attacked. I'll show you the mechanism in just a bit, but the way you want to do this is that pretend that O- is attacking that dot, kicking out the leaving group. This should look familiar for those of you who remember substitution reactions. If you remember alkyne alkylation, right, when the alkyne anion attacked an alkyl halide, this is an SN2 reaction. That's why we have this requirement. If it was secondary or tertiary, we would switch over most likely to a elimination mechanism, because the alkoxide that we're going to make is going to be also strong base. You can see that it is important that you recall some of these very important concepts in Organic Chemistry 1. Here we're talking about deprotonations, we're talking about substitutions, and we want to avoid eliminations. Okay. All right. Maybe if I draw you the mechanism, it would be a little more clear. So let's do that. First step is a deprotonation, and we're going to use sodium hydride. Now, you should understand that when dissolved in solution, the sodium plus and the H- will separate, and our base is going to be the H-, the hydride. Okay, I drew the bond between the oxygen and hydrogen because you explicitly have to show that breaking. And we get what's called the alkoxide, the alkyl oxide, the alkyl group, and the oxygen. Now that alkoxide could act like a nucleophile or it can act like a base. But when you react it with a primary alkyl halide or a methyl halide, something that's very uncrowded, it's going to attack and kick out the leaving group and act like a nucleophile. We also produce H2 gas. So that's good because we can't have any reversibility when you produce gas, because that bubbles out of the solution and evaporates. So we get a very high yield of the alkoxide, and then we do our second reaction. We add the alkyl halide. And when we add the alkyl halide, I'll draw it this way. It's substitution. we're going to substitute the bromine for this alkoxide. And that's how we add what's called the alkoxy group, right? The alkoxy group that was added was the group on the right. All right, so let's finish up this mechanism, and we have this dot that, and we kicked out a Br minus. Okay. This is obviously a deprotonation, this step right here. But what is this step? It's a substitution, but you notice that the leaving group needed help to be kicked out. It doesn't leave on its own. You know that as a SN2 substitution, right? We're not making a carbocation. We also should realize, again, that this is primary. Okay. What I want to do is analyze the reaction, the first reaction that we've seen, and what bond do we make? Did we make the bond on the left or the bond on the right? In this reaction, we made the bond on the right. But do you realize that if we're not shown the starting material and we were asked to make this ether, what's to prevent us from making the bond on the left? Okay, let's see what that does. So suppose you want to make the same ether okay, but now we want to make the bond on the left. We call it bond A or via bond formation here. Well, if you have a note card, or I'm just going to use a piece of paper. If I'm making the bond on the left, my alkoxide should look like this, right? The O minus should look like that, not like that, okay? And then what is that alkoxide attacking? It's attacking an alkyl halide. Ooh, that looks like that, okay? Looks like that. Actually, that might look good. Because now we're attacking this carbon right here. Okay. So what alcohol are we going to use? We're going to use this alcohol. I'm going to draw it. Man. So I flipped it over. So I'll draw it like that. There are other ways to deprotonate the hydroxyl group. Another strong base could be sodium amide, NaNH2. Right? We've seen that before when we were deprotonating terminal alkynes. And we get this O minus. What alkyl halide are we attacking? Okay, we're attacking that dot right there. So here's your alkyl halide. Oh, I wasn't planning on this, but this looks good also, right? Because that is still primary. It's crowded on the what's called the beta position, or you could call this beta branching, but we could still consider this a good alkyl halide to do the substitution. And we finish the product and double check that it's a target that we want. Yeah, it's the same molecule, I just flipped it. Okay. I wanted to show you a method that wouldn't work. Okay, let me show you this problem. Let us make a new ether, and we're going to have to decide what alkoxide and what alkyl halide we want to react to make this ether. Okay, so here's a practice problem. Make target via Williamson Ether Synthesis. And the target is going to be this one. Your choices are either to make the bond on the left, the bond on the right, or it could be possible to do either one. We'll call this bond A, and we'll call this bond B. This exercise is probably familiar to some of you if you remember how to alkylate an alkyne, right? And then we look at a targeted alkyne and we decide, do we make the bond on the left or on the right? We're doing the same situation here, and just like before, we're going to try to figure out what kind of alkyl halide we would need to attack to make the product. Now, some of you may know how to do this the quick way, but I'm going to show you how to use scratch paper to figure this out. So to make bond A, okay, we have to use this alkoxide right here. Let me copy that. Plus an alkyl halide. That alkyl halide looks like that. See that dot? That's where the bromine should go. Okay, that's one way. The other way is if I want to make bond B, I need an alcohol that will give me an alkoxide that looks like this. And I want to attack an alkyl halide that looks like that, where the bromine's attached to the dot. What do I notice here? I notice that the alkyl halide I have to use to make bond A is primary, and the one to make bond B is actually secondary. What that means is that this method will not work to give me this ether. Okay, but this is not the answer. The answer is show how to make this target via Williamson Ether Synthesis. I want to show starting from the alcohol. Okay, that's what I would expect. And so here's my alcohol. Okay, and we want to do a deprotonation. We've already seen NaNH2 to deprotonate. We've also seen hydride to deprotonate, typically written out as sodium hydride, NaH. There's one more way that I want to mention. You could use any group 1 metal to deprotonate. For instance, lithium. It's lithium 0. It's neutral. It's not lithium ion. It's not lithium plus. We don't have technically a base to grab the hydrogen. But when you mix an alcohol with just a metal, okay, a group 1 metal, you will be able to remove that hydrogen. It's not by any mechanism that I've shown you before. Okay, so you don't need to know this mechanism. And we get O minus. Okay. If you're curious about this reaction, technically, you would need 2 molecules of the alcohol and 2 molecules of lithium, because what you end up making actually is this. You're making H2 gas again. Okay, so do you see how we needed 2 of these molecules to give us our 2 hydrogens? And that would give us 2 alkoxides and 2 lithiums. So this part, there are 2 of them. Okay. But we're typically not worried about balancing the reactions when we draw out an organic reaction. Okay. Oh, still doing the synthesis. So here we go. We have that alkoxide, and then the second reaction is this. Oops, Br dot. So you didn't see that. Dot. Okay, that is our target. Check. Okay, that was strategy to make bond A. Check. What happens with if we try to do this? Okay. Let me remind you that O minus, that alkoxide, yes, it could act like a strong nucleophile, but it could also act like a strong base. And when you have a secondary alkyl halide, okay, like this, when it's crowded, when it's secondary or tertiary, it's less likely for the O to be able to attack here and kick out the bromine. It's more likely to rip off one of these beta hydrogens. So when your alkyl halide is secondary or tertiary, the reaction that will actually happen is this. What is this reaction? This is an elimination. And all we did was we reprotonated the alkoxide to get back the alcohol. Okay, so that's nonsense. Like, that didn't accomplish anything. And we also made an alkene. Okay. Now we could have made the alkene to the right to put the double bond on between this carbon and the beta carbon here. So there's a mixture of alkenes. But definitely we did not get the product that we were trying to target. Okay. All right. If we look at, let me zoom out a little bit. Okay, if we look at our two options, what happened here, because this is primary, we did an SN2 reaction. But when it gets more crowded, here where it's secondary, what did we actually do? We made a product that came from an E2 mechanism. Okay, that's Williamson Ether Synthesis. We could also try this at home. Again, the question is how would you make, and let me take a look at this ether. How about this? How would you make that ether from an alcohol? Okay, and you'll do that on your own. All right. What else I want to talk about here? This is Williamson Ether Synthesis. At the beginning of the video, I said this was the preferred way to make an ether. There are other ways in the textbook to make an ether. Let me show you a couple of those, but for my class, if I ask you to make an ether, I would always expect you to do it via Williamson Ether Synthesis. All right, so let me show you other ways that are in the textbook. One way is to, let's see, other ways, or maybe just one other way to make ether. Let's say if symmetrical. Let's do dipropyl ether. All right. We have plenty of time. Dipropyl ether. Symmetrical in the sense that both R groups are identical. Do you know how to name this by IUPAC? This would be what? This would be propoxy. Oh, sorry, 1 propoxy. 1, 2, 3. And we'll make the left side the substituent. 1 propoxy, no space, propane. Okay. Common name and IUPAC. Okay, enough of that. If it's symmetrical, what you could do actually is you can take take the alcohol equivalent. Okay, can you see how this could possibly be this part here? All you have to do is remove this H, and you add acid. Okay. And I'm just going to put here too. Okay. Now you got to be a little bit careful. Honestly, I'm not going to, for my exams, I'm not going to ask anyone to make an ether this way, because what should my student think of when they immediately see alcohol and sulfuric acid? You should think about acid catalyzed dehydration, right, to make the alkene. So the danger of this is that under almost the same conditions, okay, I know we usually use heat, you would get this, right, the dehydration. Okay, I'm not going to say how to control the reaction conditions to get the ether versus the alkene. Okay, that's beyond the scope of this video. But what I do want to show is how. How could we get an ether by using the same conditions where we would expect to get the alkene? Okay. In real life, it's actually a temperature control. I'm trying to think of which one is the higher temperature. I think the dehydration, if you blast it with high temperatures, you'll get mostly alkene, and then at lower temperatures, you'll get mostly ether. But that's not what I'm really curious about, whether you know or not. What I'm curious about is, if I get the ether, do you know how I got there? All right, so let me show you the mechanism. Would I ask this on an exam? Most likely not, but would I expect you to know how to take concepts from different units and combine them into a mechanism? Definitely yes. So this is a practice to see if you could take concepts and mechanisms from different parts of the textbook and put them together to create a new mechanism that you've never seen before. Well, take a look at this. Well, maybe, this oxygen has to have come from one of these alcohol groups. So what bond are we making? It's possible that we made possibly, this bond right here. Okay. But what does that mean? Normally to do that, wouldn't you need an alkyl halide? But we don't have an alkyl halide. We have an alcohol. We got to make this OH a good leaving group. Okay. Whenever you have sulfuric acid, you could assume that you have a little bit of water, and the water gets protonated, and you could do a protonation that way, using hydronium as the acid. What's the purpose of this protonation? The purpose of this is to make this a good leaving group, so we could have an attack. Attack by what? Well, we got to get another R group onto that molecule. So why don't we do this? You see that we can't do a deprotonation. We're under acidic conditions. You wouldn't deprotonate anything under acidic conditions. All you would do is protonate something. So we have that to work with. We can't make the alkoxide. But we know that this is a nucleophile. It's a weak nucleophile, but it's still a nucleophile nonetheless, and we could have this attack. and we can kick this out. Let's see if we get anywhere close to the product. O. Okay, that hydrogen is still on the oxygen right there, and it's positive. Okay. We kicked out water. Great. It's good that we kicked out water because we don't have to redraw it over the arrow. We could just use the water that we created to deprotonate our ether. And we created another hydronium ion. Okay. So it does look like that it is catalytic. Catalytic. Okay. Okay. There's one last thing concerning Williamson Ether Synthesis. Okay, so there's a problem where I may not ask you directly how to draw the mechanism for this, but again, the concepts are important that we understand that if we could figure out what's the nucleophile, what's the electrophile, where is the leaving group and how does it leave, we can make a lot of different molecules from reactions that we've never seen before. Okay. The reaction that I want us to do, or the synthesis, or sorry, the mechanism that I want us to figure out is this one right here. NaH maybe, and when I take this, it's a molecule with two functional groups, a hydroxyl group and a halide. And when I add base, something strange happens, or at least it initially looks strange. We get this cyclic ether, right? Cyclic ether. But we have, even though this is a new type of ether, and we've really only learned one way to make ethers, which was Williamson Ether Synthesis, we have all the components. We have an alcohol, we have an alkyl halide, and we have a base to deprotonate that alcohol. So my task is how. Show how with a mechanism. Okay. I'm saying that this is the product when we do this in lab, but I want to know how does it happen. Maybe this is a little bit unexpected. So it would be our job to propose a mechanism to see if it's reasonable that this is the product. Okay. I will actually let you do that on your own. All right. The one trick that I'm showing is this dot right here. I like to put a dot actually on the carbon that's being attacked because I know there had to have been a key bond made to close the ring. Let me just make sure that this is the right product. Oh, yeah, this is the product. Okay. All right. Good luck with that. I think the next video we are going on to epoxides. We are done with now the ethers. All right.